This presentation describes the stroboscope random number generator, the associated statements, and functions. Understanding how the stroboscope random number generator works is very important for implementing variance reduction techniques that will be presented later. The stroboscope random number generator formula is shown here. Stroboscope uses a prime modulus multiplicative linear congruential generator that takes as input an integer random number and produces the next integer random number. The initial random number is multiplied by the multiplier shown here, and then stroboscope performs a modulo division where the modulus is the prime number 2 to the 31st power minus 1. The result of this formula is the next integer random number. The new integer random number then becomes the input to the formula, which produces the next integer random number. This process then continues to produce a sequence of integer random numbers. This generator was found to be among the 5 best available according to Fishman and Moore. The initial value, integer random number 0, can be any integer in the range from 1 to 2 to the 31st minus 2. The generated sequence of integer random numbers is a sequence of 2 to the 31st minus 2 integer random numbers. This generated sequence covers all the integers from 1 to 2 to the 31st minus 2 without repeating any integer numbers. The sequence of integer random numbers is both a fixed chain and a closed chain. It is a fixed chain because each integer random number is always followed by the same integer random number, like rings in a chain. It is a closed chain because when the index I exceeds 2 to the 31st minus 2, the chain of integer random numbers is repeated exactly as before. In most simulation models, this does not happen because the sequence of integer random numbers is so long. It has over 2 billion numbers. Stroboscope's closed chain of integer random numbers is shown in this figure. The initial value, IRN0, was chosen arbitrarily. Each box in this figure shows a particular position in the chain of integer random numbers, with position 0 occupied by the initial value of the integer random number sequence. This is followed by position 1, position 2, etc., until we arrive at position 2 to the 31 minus 2, which is identical to position 0. Each box shows the integer random number that corresponds to that ring in the random number chain, and also shows the corresponding random number in the range from 0 to 1. The random number in the range from 0 to 1 is found by taking the integer random number and dividing it by 2 to the 31 minus 1. The important thing to appreciate in this figure is that if one starts at any position in the chain of integer random numbers, then the sequence of integer random numbers that follows is fixed. It does not change. And eventually, this sequence will be repeated if one continues long enough and exceeds 2 to the 31 minus 2 integer random numbers. The starting position that is used in a stroboscope model, that is IRN0, is defined by the statement seed that is used in the simulation model, which is as follows. The argument initial IRN can be any integer number in the range from 1 to 2 to the 31 minus 2. It is this seed, which is the initial random number, that determines the sequence of integer random numbers that a simulation model will actually experience. This means that if two simulation runs of the same or different models use the same seed with the same number, initial integer random number, then they will use the same sequence of integer random numbers. This is very important for the subject of variance reduction that will follow. The corresponding random number in the interval 0, 1 is obtained by division. That is, the integer random number in position I is divided by 2 to the 31st minus 1, and that results in a random number in the position I, which is between 0 and 1. Notice that these random numbers in the interval 0, 1 do not include the value 0 or the value 1. We shall now describe Stroboscope's statements that control the random number generator. The first statement initializes the default random number for stream 0, which is the default stream. The syntax is the statement seed followed by an integer between 1 and 2 to the 31st minus 2. For example, seed followed by the number 9111964. The seed statement sets the initial random number at position 0 for the default stream only. A seed statement that is executed after a streams statement does not affect the non-default streams. This will be described in the next section. To define additional random number streams, we use the statement streams followed by the number of additional streams. For example, streams 3. This statement creates additional non-default streams 1, 2, and 3. So in total, we will have 4 streams, including the default stream 0. Statement streams first destroys all previously existing non-default streams. The statement streams then creates number of additional streams in addition to the default stream, which has the number 0. The additional streams are numbered from 1 to the number of additional streams, for example, from 1 through 3. By default, each new non-default stream k points to a ring that is 100,000 rings away from the ring pointed to by the previous stream k-1 in the integer random number sequence. By default, up to 100,000 random numbers can be retrieved from stream k before starting to reuse the random numbers already retrieved by stream k plus 1. This does not happen often, but care should be taken so it does not occur. By default, the maximum number of completely independent streams is 21,474, which is determined by dividing 2 to the 31 minus 2 by 100,000. The additional non-default streams are used every time Stroboscope evaluates any of the statistical sampling functions that take a stream number as an argument. For example, srand, snormal, spert, spertpg. These functions will be described later. These functions are similar to the functions that use the default stream 0. The difference is that the letter s is prefixed to their names and that they take one extra argument that specifies the stream to be used, which can also be stream 0. A very useful statement for initializing all random number streams from 0 to k at the same time is seed all, which takes as an argument an integer random number from 1 to 2 to the 31 minus 2, and then an optional number that is the separation in hundreds of thousands between successive streams. For example, seed all followed by an integer number and then followed by the number 4. Or another example is seed all followed by just an integer number. The seed all statement initializes the starting location of all defined streams. The default stream 0 points to the ring whose integer random number is the one used in the seed all statement. The remaining streams are separated an equal number of rings from each other. That separation is the number 100,000 multiplied by the separation in hundreds of thousands. If the separation in hundreds of thousands is not specified, it is assumed to be the number 1. In the first example, the default stream points to the ring with integer random number 9111964. The remaining streams point to rings that are 400,000 rings apart, because the integer number 4 multiplies 100,000 and gives us the separation of 400,000. In the second example, the second argument to seed all is missing, in which case we have a similar declaration, but the streams are separated by 100,000 rings. If we wish to initialize a specific random number stream, we can use the statement seed n, which takes as an argument the stream number followed by an integer. For example, seed n 12 followed by an integer seed. The seed n statement points the non-default stream number to the ring with the integer random number supplied as an argument to the statement. The above example points stream number 12 to the ring with integer random number 9111964. All other streams remain pointing to their respective rings. The global variable car seed returns the integer random number to which the default stream currently points. Car seed is a predefined system-maintained variable which is available at all times. This table shows Stroboscope's random variate generating functions. Each one of these functions returns random numbers from a specified distribution, such as beta, Erlang, exponential, gamma, normal, etc. Each one of these functions takes as arguments the parameters of the distribution and an optional argument, s. The notation s in curly braces indicates that the function argument inside the curly braces is optional. When a function includes the optional argument, s, then it samples using stream s. For example, exponential 5.7 samples using the mean 5.7 and the default stream 0, while exponential 5.7, 3 samples using the mean 5.7 and the random number stream 3. The ability to sample variates using particular streams is very important in variance reduction. That subject will be described later. Notice that for backwards compatibility with previous versions of Stroboscope, the random number functions that use streams can also be written with the prefix s before the function name. For example, we can write uniform, low, high, s, or we can also write s uniform, low, high, s. The last column, random numbers used, indicates how many uniformly distributed random numbers in the interval 0 to 1 are used to generate one random variate for each distribution. For example, for the S-normal distribution, we use 2 random numbers to generate every other sample. How many random numbers are used to generate one random variate depends on the implementation of the particular function. For example, the normal function uses a variable number of random numbers between 0 and 1 to generate one variate from the normal distribution. The S-normal uses a different approach and uses two random numbers every other sample. If we use the normal inv function, to which we supply the mean, the standard deviation, and a random number, then we can make sure that only one random number is used to generate one random variate from the normal distribution. Which version of the normal distribution we use depends on which variance reduction technique we would like to use. This table shows special random variate functions. The first one, last RND, is particularly important because it returns the last random number that was retrieved from the default stream in the range from 0 to 1. It is often used to retrieve the last number retrieved by the function RND. If a random number has never been retrieved from the default stream, then last RND returns the value 0. Last RND with an argument S is similar, and it returns the last random number retrieved from stream S. If a random number has never been retrieved from stream S, then S last RND S returns the value 0. The function sSeed with an argument S returns the integer random number of the ring to which stream S is currently pointing. Notice that sSeed with an argument 0 is equivalent to car seed. The last function, offsetSeed, can be used to seed streams in models that require very sophisticated stream control. However, it should be used sparingly because it is very slow. The next table shows the random number generator statistical functions. The first statement, antithetics, shows the status of the system antithetic sampling generation. This is something that will be described in variance reduction later on. This is followed by the confidence statement, which returns a half-width of a confidence interval, the normal inv function, which returns the inverse of the normal distribution, the std normal inv, which returns the inverse of the standard normal distribution, and the tinv function, which returns the inverse of the t distribution. Notice that these functions do not return random numbers, they are deterministic functions. The statements here describe a stroboscope model, which is very useful for understanding the stroboscope random number generator. This example makes use of many of the statements described previously. The output of this model provides the integer random numbers and the random numbers from 0 to 1 that was used to create the figure that was described previously. This page shows the output of the stroboscope model. The beginning part describes the integer random number formula used by the stroboscope random number generator, provides the values of some important numbers involved in the stroboscope random number generator and its length, and the remaining of the output reproduces the numbers that were used to create the figure that was shown earlier, illustrating the stroboscope chain. The first column shows the position of the integer random number, which starts at 0 and then wraps around to 2 to the 31st. The last column shows the corresponding integer random number, which starts with the initial seed in position 0, which is then repeated in position 2 to the 31 minus 2. The third column takes the integer random number and divides it by 2 to the 31st minus 1. That is the corresponding random number in the range from 0 to 1. The second column shows the result of invoking the RNG function. Note that the second column and the third column produce the same results except for some particular cases. When position is 0, for example, we cannot get a result from the RNG function because as soon as we invoke it, the integer random number will advance to the first position and we will obtain the first result from the RNG function. The same is true when we try to access the integer random number at position 100,000, 200,000, and 300,000. The bottom of the table shows how antithetics work. When we instruct Stroboscope to use antithetic sampling, the sequence of random numbers in the last column is still the same. However, the results of the RNG function are not the same as in the previous table. They equal 1 minus the RNG results in the previous table. For example, the result of the RNG function in position 1 equals 1 minus the result of the RNG function in position 1 when antithetics are turned off. Newcomers to Stroboscope are well advised to study this example to understand how the Stroboscope random number generator works and how one can use the statements to control the random number generator.